Okay, so we're recording. So good morning, everybody. Welcome to ONOS TST meeting. Today, the agenda is to go over, basically do an update on a past milestone, which was primarily focused on clustering. And so so also let me remind you that this is a public and recorded meeting. I'll be posting this later on YouTube. And so given that this was focused on clustering, I'm going to pass the baton straight to Jordan. Jordan, would you prefer to share, or do you want me to just go through the, help you go through these?
You can stay here. Yeah, you can share.
Sounds great. So let's dive into that one first.
Yeah, so this sprint was sort of focused on just trying to get clustering to work, clustering in HA. And so we finished what I call a naive implementation of clustering. It sort of is not too concerned with meeting our latency benchmarks. We just wanted to get it working and then improve it from there. And so there are two components to this. Well, there's Mastership, which I'll talk about in a minute, which was in there before this sprint. And then the two stores. So the indication store is the store that was already in ONOS RIC. Basically, it's used to propagate notifications coming from the southbound up to the northbound. And that's still implemented the same way. It's implemented with an atomics map that's backed by a distributed cache. And sort of east-west propagation is done via the primitive. So basically, well, I'll show a diagram in a second, but basically events or east-west communication is going through some separate service, which is the distributed cache, which it can be inefficient for our purposes. And the request store the request store is something that I added to basically do the opposite. When there's, for example, a handover request that arrives on the northbound, it needs to be propagated to the appropriate node and then sent on the southbound. And so that's done similarly, but with a distributed cache, but with a different primitive. So in the case of requests, like a handover request, we have to make sure that they're being processed in the correct order, and in the event of a failure, they're being handled by some other node. And so this is handled by a sort of distributed log, which the distributed log is a primitive that Adib added that allows you to append messages to a queue and acknowledge them. And so they get persisted in this distributed cache until they're processed and sent on the southbound. And so that's done by masters. And then, yeah, and this is the sort of naive implementation of clustering, which basically consumes all of our latency budget when I've tested it. So just to show what this looks like, you can go to the next slide. Yeah, so like I said, there's Mastership. So the way that ONOS RIC communicates with devices on the southbound is the same as we've done with other controllers. So there's a Mastership election, which the Mastership election is backed by consensus. So we have a RAF cluster running alongside ONOS RIC, which we use for Mastership election. And the problem is that once we get to multiple nodes, an application on the northbound can be connected to one node, while another node is the master for a device. And so we have to have a way to propagate data across them. So you can go to the next one. So for example, when something that uses the indication store, like metrics coming from the network, when they go up to ONOS RIC, to the ONOS RIC master, they get stuck in the cache, and the primitive does its work and distributes it, so it can be propagated up to applications. And if you go to the next one, the same is true if an application sends a request to ONOS RIC that it wants to be sent to a device, for example, handover. That gets stuck in the cache and propagated. But this is really inefficient, especially for low latency applications, which is why I call it naive. And so the future work on the next slide is to recover that. And so that's what I want to do in the next sprint. So recover the lost handover latency the handover latency that we lost due to this work. So last TST, I talked about the membership API, which enables us to do faster peer-to-peer communication and not having to have all the east-west communication go through an external service. And so the plan is to use that, replace the distributed cache backend with lower latency peer-to-peer protocol that should recuperate the vast majority of that latency, and then reduce the overhead. There's some other unnecessary overhead in the east-west communication that also needs to be resolved, and then just improve and verify the consistency and HA of the new stores. So one idea was to introduce an intermediate data model that's more suitable for concurrency control. Like currently we're storing, basically storing the southbound messages, but some of them are not well suited to storage, and trying to figure out something like which master or which node is the master that should handle a request and things like that. And so we at least need some, I think we're probably going to need some data model just for the stores to, that they can use to basically optimize communication, east-west communication. And then we still need to do like HA testing. So add HA tests for failures of devices and for failures of the ONOS RIC nodes themselves. So that's the plan.
I see. Also, do we want to do some server-side filtering, or potentially even?
Yeah, so that's what I was covering in the optimize east-west communication to reduce overhead. That's what I was thinking about.
Okay.
Is fixing that particular problem, because currently a ton of data that is being unnecessarily sent between the nodes, and especially since we're trying to achieve low latency, that's just something that's easy to fix, and we don't gain anything by sending a bunch of data that we're not using. So
right, no, makes perfect sense. And I think Oz was also alluding to the fact of being able to do some server-side computation. Right, so basically it's like a filtering.
Oh yes. Oh yeah. Oh, I see. Yeah. Yeah, I think we'll have to think about that.
Yeah, for sure. Well, thanks, Jordan.
Hey, Jordan. Sure. Some very basic questions for my understandings. How does the distribution happen? Like assume the base stations are distributed across the nodes.
Yes.
And that would happen when the base station is configured. Like from topo, we get the information that there's a new base station.
Yep.
And that's when the distribution happens, I guess.
Exactly. Yeah. So when ONOS RIC learns of a base station, each node as it learns of it, it will join a Mastership elections, and the Mastership election is another atomic primitive that uses consensus to basically assign control of the device to some ONOS RIC node. And so that's how they coordinate with each other. And it's fault tolerant. So in the event that some node that's controlling a device crashes, the consensus algorithm automatically assigns Mastership to another node. And so this is the role of Mastership. This is how, this is how it's just spread across the ONOS RIC.
Oh, so when you say Mastership, it's Mastership. Each node can be is a master for a set of base stations.
Correct. Yeah.
Right. Okay. And how do you determine, like, let's say your slide number 6, I guess I can't see it very clearly here, but there's a message that comes from the device, and how does the cache determine to which how does the cache determine the master from the message?
That's a good question. So, so this is just something that's baked into atomics primitives. There are features atomics primitives that provide sort of events distribution. So basically, when a master gets elected, it tells it basically subscribes to events from the primitive, from the relevant primitive, and then when some data is stuck in that cache, basically it distributes it to any node that was listening for it. And this is where the problem with this is part of the reason that I said we were sending a lot of data that was unnecessary, because currently basically every piece of data that gets stuck in the cache gets sent to every node, and that's incredibly inefficient. And so if you're a master, or any node will always get all of the data currently. They just filter it out. So master just listens for all the data, and it just filters out whatever data is relevant to devices that it controls. And so that's something that I need to fix.
Right. Thanks.
Yeah, we're gonna do basically, yeah, it's gonna look like a multicast tree, right?
Yeah.
At a later time. So the data only goes where it needs to be, where it is consumed. All right, any other questions for Jordan? If not, thanks a lot, Jordan. And I think we can move to cover the RAN simulator enhancements. I think, Sean, you're going to take that, right?
Yeah, I'll take that one, Thomas. You can stay presenting. I've only 2 slides. So if you move to the next slide. So one of the big enhancements for this milestone was having a number of sectors per cell tower. So in this diagram, as you see here, there are 4 cell towers marked with the A, and then each one of those has 3 sectors. So we're showing a beam here. Now the beam really is just an approximation of what's happening internally in the simulator. Really, it's just for display purposes. So basically, inside the simulator itself, you know, it's mimicking these UEs, and for each one of them, it's calculating based on 2 things: the intensity of the signal that might arrive at that UE. So it's based on distance, and it's based on an angle compared to the beam angle. So say, for instance, this car, I don't know, in the left-hand most car there, I can't really point at it, but you know, you can see, well, that's probably not a good example that needs to be handed over, but there's a calculation going on per each UE to figure out which cell it belongs to, and well, with what the intensity is at each UE, send it up to the handover application, and then that tells it which cell it should belong to. So as part of the approximation, there's like the dotted line here is like a line to the centroid of the beam, and you know, that's basically showing you you know, where the effective center of the beam is. So there's a line drawn from that to the UE to kind of show the affinity it has to each cell tower. Really is for display purposes, for demoing. So the dynamic, the guitar pick shape is really generated from like B-splines, and it's like it varies on the beam angle. So you might have 6 sectors per tower, and you know, it'll draw a beam that's kind of half the width. And also the beam size varies on the beam strength. So you can see the one on the bottom right is much bigger than the one on the bottom left. That's because the load balancing application is increasing the size or the strength of the signal. And so the idea is that the UEs within its region will pick up on that. So let me see the second enhancement then, if you go on to the next slide, Thomas. So this was about how we can integrate the simulator with ONOS config. So going between ONOS RIC and the simulator is the E2 interface. And that's really about the handling the control of the cells, but there's also configuration needed on each one of the cells. So basically, what happens is each cell on the simulator now exposes both the E2 interface and the GNMI interface per cell. And so basically, when the system starts up with the umbrella chart, it starts up all of these 4 microservices, and RIC, config, and RAN simulator listen out to ONOS topo for a list of devices. And currently, the devices are loaded once everything else is up and running, and so the simulator, will hear about a new device. It'll set up a cell for us. It'll put it in its location, and then it'll start an E2 interface and the GNMI interface. And config also listens to topo and starts distributing those GNMI configurations to the cell. And then RIC realizes there's a device there, and it connects over the E2 to the RAN simulator. So the startup procedure has changed a little bit from the previous distribution, and now it's effectively allowing us have GNMI and configuration of the RAN simulator in the process as well. And the point here with this E2 node is this is a Yang model that was developed for configuration attributes on the E2 node, and that's basically plugged into the ONOS config, giving the end user the the full configuration experience for the E2.
Hey, Sean.
That's it. Any questions on that?
Yeah, Sean. One question. When you say cell, do you mean cell is that guitar pick thing, or is it like a set
Yes,
of three
yeah.
guitar picks?
No. Each beam is a cell in itself.
Okay.
So yeah,
And
I was dealing with. Sorry, go ahead.
Oh yeah. So follow-up was when you make an E2 connection when the between the RIC and the E2 node. So that E2 connection, does it signify one cell, or does it signify the E2 node which comprises maybe the three cells?
So it's no, it's dealing with each sector or cell is an E2 node at the moment.
Okay. So
they're operating independently totally, Shad.
Okay. Maybe this is something maybe we want to take a closer look at. Even I don't know perfectly well, but my understanding is that
absolutely we can, if there's an object we want to model for the tower, really the tower isn't. We're not even modeling the tower anymore. We're really just modeling the cells, and it's as if there is an E2 node for each sector on the cell.
Yeah, because I was under the impression that the RIC is talking to the CU CP, and then the CU CP then talks to the DU, and the DU then is connected to the RUs, and the RUs are actually the antennas, and they are the beams and all that stuff. So we could be talking to an E2 node which is actually comprises of the three guitar picks.
Yes. Okay. I understand.
Okay. Yeah. So I mean, just something to note, and
we can add as an enhancement.
Sure.
All right. Any other questions for Sean? All right. Thank you, Sean. So I think next we can move to the enhancements of the handover application. Wujan, do you want to take that? Do you want to present your own, or do you want me to go through this?
Yeah. Let me share my screen.
All right. I'll stop sharing. Right, we see you, yeah.
Okay, so hi, this is Sujung, and I'm here to introduce the new Handover application enhancements. It is an A3 Handover application. So before we start, we have to check what application we have used. It is very naive Handover application. So at the run side, it generates a telemetry message which has serving cells CQI and some neighbor cells CQI for each UE. It is a per UE message. And once those messages are generated, the run side transmits those messages to ONOS RIC core periodically. And after receiving telemetry messages, ONOS RIC core directly pass all of them to Handover application. And at the Handover application side, it calls a Handover decision maker for each telemetry message. And this decision maker simply compares CQI values for a telemetry message. If serving cell is still good, then handover will not happen. But otherwise, this application sends a handover trigger message, handover request message for the telemetry message to ONOS RIC core. But it is really a simple application. It just compared the CQI values for between serving cell and each of neighbor cells. So it's really simple. And well, looks like it is a bit effective, but it does not have any realistic features. So I upgraded this application considering with 3GPP standard and some research topics. So in the 3GPP standard, there are so many handover events type. Among them, we have to focus on the A3 event here. This event is typical and normal handover event, which we are thinking. But to handle this handover events, we have to prepare 3 handover parameters: hysteresis, A3 offset, and time to trigger value. I will simply explain each parameter here. And so here, let's assume that, well, here is the handover scenario. So let's assume that there are 2 inode Bs and 1 UE. And this UE locates in the middle of 2 inode Bs and it is not moving. At this time, a handover event will happen frequently with the naive handover application because, well, radio channel is fluctuated rapidly. It is it is like a physical stuff, so it happened. Here is this graph is an example of channel fluctuation for the above scenario here. And as you can see, there are some handover events with the naive application. So at this point here, since inode B1's channel quality is better than inode B2, so handover will happen here. At here, well, inode B2 channel quality is better, so handover will happen here. So every intersection handover will happen, and the number of handover events are 1, 2, 3. Number of handover events is 1, 2, 3, 4, 5, 6, 7, 9. So at this scenario, the number of handover events is 9. And let's apply the A3 offset first at the same scenario here. So A3 offset is just the offset to increase RSRP or CQI value. So in this figure, I only increase the inode B1's RSRP by the offset like this. So the number of intersection decreases. Now it is 1, 2, 3, 4, 5, 6. So this means that the number of handover events changed from 9 to 6. So, well, handover events decreases. And let's apply time to trigger plus A3 offset. So it is sort of just time to trigger is a timer, just a timer. So if a UE requires a handover event, then timer is just started like this here. But handover will not happen at this time. After timer is expired, then handover will happen like this. But in the meantime, I mean, when timer is ticking, but channel quality is changed like this. For example, at this point, inode B1's channel quality is better. But at this point, B2's channel quality is better. However, timer is not expired, handover will not happen. So this is just like a guard interval. So with this time to trigger, the number of handover events is just 1, like this. And let's apply the hysteresis value here with H3 offset and time to trigger. Hysteresis is just a margin value, and with this we can achieve more robustness from a frequent channel fluctuation environment. So with hysteresis, timer will start at this point here, at the upper margin, and well, this event will be finished at the lower margin here. So this is hysteresis margin. This figure is actually not a good example to explain the hysteresis, since hysteresis is much more effective in more and more rapidly fluctuated channel quality situation, but it gives us some of robustness from the channel fluctuation. So this is hysteresis margin, and our new handover application called the H3 handover application has those 3 parameters. So here is the figure to explain how the H3 handover application is running. And at the time slot 0 here, there are 5 telemetry messages. And each telemetry message has those information. So once those telemetry message arrives from ONOS RIC core, then C1 interface in handover application pass them to the decision maker here. And decision maker calculate the CQI delta value, which is defined in the 3GPP standard. And let's assume that UE4 and 5 has the negative CQI delta value, which means that serving cell is better than all other neighbor cells. So except them, decision maker make 3 H3 events for those 3 UEs, 3 telemetry messages here. So serving cell and target cell is same as this information defined in the telemetry message. And H3 events has a timer. It has 10 milliseconds. It just started. And let's move on to the time slot 1 here. And handover application also received those 5 telemetry messages for each UE. And there are some changes. For UE1, target cell is changed to 0001, which is the same as serving cell. This means that it is exactly same situation here. So this situation. So the B1 is getting better in the timer. So this means that handover will not happen here. So this H3 events timer will expire. H3 events turn off their timer and shut down this for routine. And UE2 has the same information as the previous times, the telemetry message received at the previous time slot. So timer is still ticking here like this. Previously it was 10, but now it is 5 milliseconds. And for the UE3, target cell is changed from 7 to 8, which is not the same as the serving cell. So in this situation, this target cell is changed from 7 to 8, and timer is reset. So this is the event for UE3 telemetry message. And at this time, UE4, for example, UE4 has negative CQI delta value. So at this time, decision maker make 1 more H3 event for UE4 telemetry message. And UE5, if UE5 still has the negative CQI delta value, then it was discarded. It is time slot 1 at T1. And let's assume that, of course, it is not a practical situation, but let's assume that at the time slot 2, there is no telemetry message. Then for the UE2, timer is expired. So this means that handover should happen. So for this telemetry message, for this A3 telemetry message, A3 event will make a handover request message and send it to the ONOS RIC core through C1 interface. And the other A3 events timers are still ticking. So that is how the A3 handover application is running. So I will briefly show how it works with the simple demo here. I just wrote some test code like this. Here I just, this code initialized the A3 event pool, and those are 3 parameters, and those parts is to prepare the handover channel and receivers for this test. And this function generates 3 types of telemetry message: sample message 1, 2, 3. Those are for UE ID 1, and serving cell is 0001. So at this time, for this message, the serving cell is 0001, but neighbor cell, best neighbor cell is 0002. And serving cell CQI is 15, which is the maximum value, and neighbor cell CQI is 12, which means that in this situation, serving cell is better than the neighbor cell, so handover will not happen. And this in this message, only difference is serving cell CQI. So it is worse than neighbor cell CQI. So handover may happen if A3 offset is less than 2. And with this, in this message, the only change is neighbor cell's ID and its CQI value. So the difference between serving cell CQI and neighbor cell CQI is just 1, which means that if A3 offset is more than 1, then handover will not happen. So let's run with A3 offset 0 and time to trigger 0 first. So it will make 2 handovers like this. But let's change A3 offset 0 to 1, then handover, well, this message, handover will not happen for this message. So only handover, the number of handover events is just 1. And if I change it to 3, then there is no handover events. And also let's add time to trigger value here. So in this time, so handover will only happen just 1 because so it is just exactly same situation as this one. So once sample message 2 arrives, this means that best target cell ID is set to 2, but after 10 milliseconds, a new telemetry message arrives, and which has the different neighbor cell ID. So this means that timer is resetted and target cell ID is resetted. So this previous telemetry message will be discarded, and then it is discarded, and this A3 offset A3 event is regenerated. So only one handover event happened. That is the simple demo. And with this new A3 handover application, I checked the latency. I simulated 12K UEs and 12 cells. And here is the result. So if I increase the time to trigger value from 0 to 10 or 100, the average value increases by the time to trigger value. So for example, with the 0 millisecond time to trigger value, the average was 2 milliseconds, but with the 10 millisecond, average was 12 milliseconds. It is very obvious. And if I increase, when I increase the H3 offset from 0 to 3, so in this situation, the number of handover events decreases because, you know, well, like this, since this sort of signal, so since the number of intersection decreases, of course, the handover events also decreases. That is the reason. So here is the latency measurement, and the future work is, so first, since store is changed, so I will catch up with the store and check whether the new handover application is okay or not. And I will add some intelligence on this H3 handover application to dynamically optimize the handover parameters by using machine learning or some other ways, because these handover parameters are very important for user performance or the number of handover events. So it should be dynamically optimized. That is the second work. And the last one is that some of filtering or pre-processing modules will be applied. So currently, ONOS RIC sends all of telemetry messages, and handover application should calculate delta values for all of them. I think it would be a big burden. So to resolve it, I'm thinking how to add on filter or pre-processing modules on ONOS RIC part or somewhere else. Yeah, that's all from my end. And do you have any questions or comments?
I wanted to ask Woo-Jung about the other types of handover. Do you see those being handled in the same application or a new application?
Well, I'm not sure, but I think I think I can make other events handover application at the same application, but need to study here first because there are so many events and then I need to follow up here.
Sure. And the situation where serving becomes, say, worse than threshold, like A2, is that the same as a UE going outside the range of the cell and effectively having no coverage?
Yeah. Right.
Okay. And so in this case, this is effectively telling the ONOS RIC to drop that UE, I guess, is it?
Yeah, I think so, yeah.
Okay, yeah. No, that's something that I think we will try and mimic in the next release as well. I don't think we have a threshold at the moment, but you know, that's something. If we put that in, then we will be able to get a disconnection going.
Yeah, I agree.
It almost seems to me like we ought to be able to come up with a skeleton of a handover application which remains, for the most part, kind of static, and then have almost like a state engine plugin that could be just dropped in for basically that would be using the variety of these different events depending on what one would want for the particular environment or particular policies. Because it's basically what you've described right here is kind of a state engine. Clearly, the base station deals with many UEs, but with respect to a single UE, it's basically just a self-contained state transition diagram, you know, state transition or state machine, I should say.
So I think, you know, maybe it could be in two parts. The first part evaluates what the handover event type is, and then it could hand it off to something that handles that type. Was that what you're thinking?
Well, yeah, but I mean, you could then combine it with various strategies, right? With both hysteresis as well as, you know, with the various kind of dampener with respect to the time to react, to kind of apply the procrastination strategy. right? If the situation cures itself in sufficient amount of time, there's no need to act. And but it could be just a combination of these different strategies that could be almost configured to and combine in a kind of in a combinatorial fashion and through experimentation, clearly we could figure out what yields the best result for a particular environment.
Yeah, just reading through the event types, there's a lot of different scenarios here that probably will become relevant to Ether. You know, we'll say if there is the WLAN in conjunction with 5G and so on, you know, there could be
the point I'm trying to say is the secret sauce in here, or not secret sauce, kind of the stuff of essence is what events are you interested in, or what events do you find relevant, and thus you subscribe for, and how you react to them, right? And then the skeletal structure on the outside of it it's just a generic thing. It's not unlike what we have with the reactive forwarding, where we have multiple different policies for what we can react to.
Yeah.
This is great. I was actually unaware that there were so many different events. Now, these are synthetic events, or is this something that that basically that the handover application surmises, or is this something that the base station can actually generate for us?
I think according to standard, it just the definition. I mean, it just classify those types of events, but looks like it happens at UE side, I think.
I see, on the UE side.
Right, but the UE is not the one asking for the handover. The UE really just reports the signal intensity, I guess.
Yes, so decision making is happened at node B normally.
Yeah, this is definitely a very rich field here, and this is just for handover too. All right, are there any other questions for Wujun? If not, I think that was the last item on the agenda. I think we were going to cover, we also originally were going to cover E2 enhancements and also some work on versioning, but I think we're gonna push that off. Shad has done some good work, and I would like him to be able to represent that next time around. What we will also be doing coming up is planning for the next milestone. We've already started that in GitHub for the Q2 Pronto planning, and we will also be entering some tickets on a Jira, on a Pronto Jira or Ether Jira dashboard. Are there any questions from the audience? If not, well, I think we can call the meeting closed, and the team will regroup back on Slack channel, and we'll see you next time. Thanks, everyone.
Thanks, guys. Bye.
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 Thank you.
Thanks. Take care. Bye-bye.